Hello to everyone and welcome to Urbano Canalis Essential Training Day 3. My name is Rino and today we will continue with the training from yesterday. We will talk about creating and editing catchment areas, flow calculation methods for storm and sanitary networks, scenario analysis, hydraulic calculation, pipe sizing and pipe invert optimization for gravity networks and pressure pipelines, exporting to EPA SVMM, and many other things. But before we start with the hydraulics, I will briefly show you some advanced options for plan labels and profile configuration editing. The session will last approximately 2 hours. We'll have 1 hour and 45 minutes of live presentation, and after that we will have Q&A and I will answer all of your questions. So let's start with the training. Here we are in Urbano. Here we have one really nice network, a lot bigger than the networks that we worked yesterday and day before. So maybe let's first analyze this network a little bit. I will open the data tables that we now know how to use. I will open it by double clicking on it. And here it is, all the data is here. We have everything defined like invert elevation, slopes, pipes, everything is set. And I will select the whole table by pressing Ctrl A and right mouse button on the table. And I will click here on recapitulation summary, which will give me the total number of elements and total length of the system. And we can see that this network is a little bit more than 37 kilometers of the network. So like I said already, the size of the network is not important for Urbano. You can have small networks like we had yesterday. You can have, let's say, this medium-sized networks of, let's say, 40, 50, 60 kilometers, or you can have huge networks of, let's say, 400, 500, or 600 kilometers. We've seen the systems of that size as well. But the thing I would like to show you now is some advanced options for the plan labels. So up until now, we discussed about section labels and node labels. So let's apply just some of them. I will set this length, diameter, slope for the sections. Okay, let's select the whole system. And also for the nodes, I will apply this name, terrain, and invert. Okay, so these are the standard labels. So we see this is the section label, this is the node labels. And we also learned that if we have a drop manhole, if we have multiple invert elevations, that the program will show all of them. And this is the default label. So first H invert, which is invert elevation, is the outlet. And then all the inlets are always sorted in the rotation of the clock. So this is the first one, this is this one, and this is this one. So this is just one way how you can show these invert elevations. If you want to show it by some other style, you can click here on the nodes, and here you can go to new node label and basically create everything from scratch. But also you can go here to new label from template, which will open you one dialog. And here you can check and preview some of the predefined label templates for the sections, for the nodes, for the stations, for the arrays and branches, and some specific labels, for example, for angles, for cross sections and stuff like that. So let's check it. So these for the sections are pretty basic. We covered this in the first session, but these are really important, these node labels. So it can be pretty simple. It can also be some kind of a block. This is the standard one that we already showed, but this is really interesting to me. You can have invert indexes shown on the sections, and here are the indexes showing you which value is which value. So to create it, just double click on it or select the label to create, and then you can create and edit label, or just create the label based on that template. I will click here on create label, and you see that this label is now shown here, this label configuration. So to apply it, just double click on it and again select the whole system and apply it. And now you will see this is really nice because you have the name of the manhole or the node, you have terrain elevation, and you have each of these invert indexes showing you which one is which. So this is really nice label. I like to use this type of label, but also let's check what else is available. Let's go back to nodes. Let's go to new label from the template, and let's check again. We stopped here. This is also really nice because you can have the invert elevation or also invert depth or any of the pipe elevation. It doesn't have to be invert. It can be crown of the pipe. It can be bottom of the pipe. Doesn't matter. You can show it next on the section, or you can even put the station. This is the array station in the node label, or like this. This is something that I like to use. You have the elevations here next to the sections, and you have situation like this where you have node name, terrain elevation, and also the station. Then you can also put some prefixes showing you the section name as prefix. You can also show the node, previous nodes as prefix, and stuff like that. So also some other methods where you have these prefixes showing you the X is always the outlet section, and then you have ABC is all the inlet sections. So many different types of labels can be created. And then even if for example, let's create this one with the sections by the invert elevations by the sections. Let's click on it, and you can create it, or you can create and edit it. So if you click on create and edit, you can see that everything is set from the template. And basically now if you want to add some other data, if you want to change something, position, size, leader, anything, or you can click here on this icon, invert data definition, which basically shows you how your invert will look like. So all these options, everything, so indexes, section names as prefixes, node names as prefixes, invert elevation by the section, invert depth by the section, this ABCD rule, invert elevation and depth by the section, and again this with the indexes. So if you want to apply something else, just double click on it, and that will be applied to your configuration. I will leave it like this, and let's apply it. So double click on it, let's apply it, and now it will look like this. So you have the elevation of the terrain, you have name, and you have invert elevations shown on the sections. So this is also one really nice type of the label. So it's up to you to decide what is the one that you prefer to use. Okay, these are the advanced node labels. Let's also check here. We have station labels. So I already showed you that you can put the station label in the node. So that is one way, but also we have special labels for the stations. So if you want to apply it, it's a little bit different dialog. You can define where you want to have your stations. For example, in the nodes, okay, you can also say on sections by distance step, let's say each 15 meter, or let's put, for example, each 25 meter. And again, many different options. You can select interactively positions where you would like to put them. You can also label some stations according to some polyline. For example, if you have alignment of the road, you can have this is the option, label station based on a polyline. You can take the stations from there, or many different options. I will just select this one channel like this, and I will click apply, and now you can see how this looks like. So you have the, again, name of the node and station. We have it each 25 meters, and also if you have some overlapping, you can move it by clicking here on edit, and you can move it a little bit, or also you can use automatic label reposition and also include the moving of the stations as well. So these are the station labels. Let's also check what is available. So of course you can label the entire system as well, but I will not do it now. Channel name, this is the array name. It can be, if we edit it, it can be for the arrays or for the branches. So it's up to you to define for what you would like to do it. So for array or for branch, and you can define the data, and then you can just double click on it, apply it for the whole system, or interactively put it where you would like to have it. So first I will apply it for the entire system, and now you can, so these are the labels for the entire array. So sometimes it will be placed, maybe we can put some bigger offset so that we have no overlapping. Let's put the offset of 5 like this. So let's just again select it, and I will click here. Label is drawn according to definition. This is really important option because you can move the labels. So the software is always remembering where the label is placed. But if you want to draw it according to definition, just click here on this icon. And now when we move it, basically it is here. So you can also have labels like this. So these are the names of the arrays. And if you click on interactive, you can even put it multiple times the same label. For example, like this, you can see this is all the same channel, all the same array, and you can pick and place the same labels. Also, this is really nice. It is not shown here. You can click here, or I think it's here, channel and label. So if something is not here, you can just click on the label and just create it according to template. So create channel and label, double click on it, select everything and mark it. So this will put in the beginning and in the end of each array, it will put one block. So you know that this is the start of an array. You see start of an array and end of an array. So you can also have it like this, because you can have your profiles drawn by this array definition, and then also you can mark them like this in plan as well. And also we talked about cross-section labels, that while you're drawing the cross sections, you can also, so while you're drawing the cross sections, you can also turn on to have the label of the cross section also put in the plan. Okay, the next thing that I would like to show you here is the advanced editing of the profiles. So I will select just one classic configuration of the profiles, 1000 to 100 scale, and I will draw the profiles for these three main channels, this, and I will place them like this in one column, 3 rows, and let's click on draw and let's draw them here. So I briefly showed you in the first session how you can edit these configurations. So basically just edit, and here you can add some new data. You can change the position of these columns in the data table. You can delete some data. You can basically change all the smallest detail, basically all the colors, all the data, everything. And this interactive select function allows you to basically select anything. For example, I will select this manhole, and it will take you where the options for the manholes can be set. Okay, and now I would like to show you just what are the possible, there are unlimited possibilities. Basically, your profiles can look completely different than mine looks now. So here I have some configurations in different scales, in different languages, with different data from some of our users. So I will just show you. And what is great in Urbano, you can have, for example, if you are designing a system for some different company or different investor, and you are used to work with your profile configuration, but for plotting, for giving away the project, you have to meet some standards. So it is just really easy to switch the profile configuration. To do that, I will again go to this function profile manager that we used yesterday. And here you can select a profile or all of them. I will select just this first one. And for example, first I would like to draw it in the opposite direction. Many of our users are used to draw the profiles in the opposite direction. So if you want to do it, just click here, reverse. Are you sure? Yes. And now the profile will be drawn in the opposite direction, while in the plan, your branches and your arrays will remain in the direction of the drawing. Also, if you want to change the configuration with which this profile is drawn, just click here, switch configuration, sorry, not this, but this. And now you can select any of this that is available here. Let's switch maybe to German, the same scale. Click OK. And now you see that it looks completely different. Everything is in German. You have some different colors, different data. You have also this node schemes shown here. So with this this really nice showing you where the branch is and stuff like that. So it can look completely different. Let's also switch another to show you what can also look like. One of the possibilities, for example, the Czech Republic. So again, it looks like it was created with some other software. And why I'm showing you this? Because, for example, if you have some of your configurations that you are used to work by hand or from some other software, and you are considering switching to Urbano, we can arrange for you that we create configurations for you, or of course, we can teach you to do it by using the function for editing that I show you how to do it. Also, let's apply the last one. I will use this in the bigger scale. Now this one is in millimeters. It is from the Middle East, or from our Greek users who were doing the project for the Middle East. And you can see again, some of the hydraulics data like flows, velocities, filling percent are shown here, some of the pipe data, and again, everything looks completely different. Some blocks for custom labels, you have these different colors, and everything looks pretty nice. And like I said, completely different than what we started from. Okay, so that was the first topic today. And now I will save this drawing, and we will start with the hydraulic topics. Okay, so let's just save this as final. And the next drawing that I will open is the project that we used during this training multiple times. And on this project here, I will show you how you can define catchment areas. Okay, so in Urbano, you can define catchment areas using multiple ways and using multiple methods. First of all, you can draw the catchment areas completely interactively, just like drawing a polyline, or you can convert closed polylines or just plain lines like I have here. You can see if I go to AutoCAD properties, these are just plain lines which form closed polygons. So we can convert this to intelligent Urbano objects, which are catchment areas. The third way is by just telling the software here in this section, you have a catchment area of, I don't know, 0.2 hectares. So this is also a possibility where you just input the values of the catchment areas without actually drawing them. But we will here convert these plain AutoCAD lines. So first time during this training, we are going to switch to one of these modules. I said that this is called module selection, and I will go to Canalis. So here is the Canalis panel, with all of the functions for hydraulic calculations for sewage systems. So here we have the first part of the panel, which is for the definition and editing of the catchment and the influence areas. So catchment areas are for the storm networks, and influence areas are for the sanitary networks. So for the catchment areas, you can define stuff like, I don't know, a runoff coefficient, a soil type, and some other coefficients. And for influence areas, you can define the number of people living, for example, per 1 hectare of the area. So let's go to area definition. But before, I will show you just this area label catalog. So here you can create different labels for these catchments. It can be block label or text label, and also you can define the block scale factor, whether you would like to draw it with or without the leader, and also you can define which data will be in the label, for example, like runoff coefficient, name of the area, number of people, or stuff like that. Okay, let's go to area definition. And here you can see when you open this dialog, basically everything is grayed out because the software is telling you you have to select something. So we assign catchment areas to the network elements, to the sections. So you can define that one catchment area is for one section, or you can say one catchment area is for multiple sections. For example, for an array, for an branch, for an arbitrary selection from node to node, or for multiple sections. I will go with the branches, and I will say for this branch here, we have to define now what. So I can select a point inside of a closed polygon. I can select a closed polyline, but this is not the case here. Or I can draw the closed area basically like I'm drawing a closed polyline. I will use this point option, but if you would like to use the point option, you have to use layer filtering because it basically works like AutoCAD boundary that is used for hatching, but it's not AutoCAD boundary, it's our own technology, which is much better and precise than AutoCAD boundary that they are using for hatches. So first of all, use this icon, or you can select a layer from the list. I like to use the icon to select the line or polyline or an element, and the software tells you which layer this is. This is the layer catchment areas. I will say show just selected like this, and now I will click on a point inside of this area, and the software will recognize the polygon bounded by these lines. Okay, and now the software recognized the area and showed me this data here. Before I save it, I can also define some data here. I can define the label from the catalog. I can change the name, prefix, or I can even change what is the type of this area. Is it a catchment area? Is it a house influence area or industrial influence area? I will leave it to catchment. And also I can define a runoff coefficient just numerically, or I can select from this catalog of soil types where you can define different types of the soil and assign them different runoff coefficients. I will use asphalt with the coefficient of 0.9 like this, and I will click apply so that this data is applied here. So when we click apply, this is changed and we can click save. Okay, let's continue. I will go to this branch here and I will again go and repeat the process. So this point, and now the last settings are already applied. It is asphalt with 0.9, so I will just click save. So you can first select, then edit the settings and then apply it, or you can first define the properties and then set it. So it's up to you. For example, I know that the next one that I will select will be this center of the roundabout, so I will immediately switch here from asphalt to grass like this. And now I will select this section like this, and it is for this section we have to click a point And this is it. So you see that you do not have to click on apply if you before set these properties. But I always like to check it one more time. So now you can see that for the grass, the program took from the catalog 0.3, and that's the area that we will now apply only to this one section. So before we used for the entire branch, but now we will have only for this one section. So let's click save, and let's continue now again with the branches. Now let's go to this large branch here, like this. Again, we will select a point, but it's set on grass, so I will switch to asphalt and click apply and click save. Okay, let's continue. Now I will go to this small branch here. Let's click on point, select a point inside of a closed polygon. And here now I would like to do something else. I will create a new type of the soil, and I will call it mixed. And here I will not say that the runoff coefficient is just one number. I will say that the runoff coefficient is by percentage. And I will say that, for example, we have 75% of 0.9, which is, let's say, asphalt, and we have 25% of some grass material. And now you see that the program calculated the runoff coefficient of 0.75. Let's click OK. Let's apply it, and let's save it. Okay, let's do the final one. This one here. Let's pick a point inside of a closed polygon. Let's switch to asphalt. Let's apply it, and let's save it. So basically, we started from plain AutoCAD lines, and now these are closed polylines. So these are still polylines, but they are also intelligent Urbano objects that you can label, that you can preview, that you can, I don't know, calculate and edit, rename, and everything. So that is it. So let's now open the area preview. This is a special preview which can also be used for editing, and you can start it here. So this is the, let's say, specific preview where you can filter by a type of the area. You can even set some parameters and change them and stuff like that. But also you cannot work while you have this opened, but no problem. You have this standard data previews. You can even switch back to this home panel. And here we can switch. As you can see, we have catchment or influence areas preview. You can switch to the configuration. We can select now the whole system. And now instead of nodes and sections, we see catchment areas here and all the data about the catchment areas, like names, what is the type of the area, what is the actual area in hectares, or you can put it, I don't know, in some other unit like square meters or square kilometers. You see the soil types, runoff coefficient for that soil type, and we also see the number of related sections for each catchment area. So let's turn on marking plan. So for this first one, we have 7 sections, and for this one, this is it, A3, we have only 1 section. Also, one really nice option is selection of catchment areas. So now when you hover over a catchment area, you can see this really nice tooltip showing you all the sections that belong to that catchment area, and you can see in percentages % of this one area that belongs to each section, and this is calculated proportionally to each section's length. So if a section is bigger, it will take larger percentage of that area, and if the, of course, if the section is smaller in length, it will take smaller amount of that area. And if we select it like this, we will get only that section shown here. And now, for example, if I would like to check the data about the sections that belong to that area, I can switch to some other configuration. For example, I have section configuration for catchment areas, where I have names of the sections that belong here. We have each section lengths. We have catchment area now proportionally calculated based on the section length and the total area of the catchment, and runoff coefficient for each section. So that's it. And also, if we switch now back, for example, to the preview of catchment areas, and I would like to select a section, for example, let's select this section here. In the data table, we will get all the catchments that are assigned to that selected section. Also, what is really important to say that unlike other elements, for example, I told you about nodes and sections, do not move it with the AutoCAD functions. Do not use AutoCAD move. But with the catchment areas, because these are polylines, intelligent Urbano polylines, you can also use AutoCAD options to edit them. For example, you converted some polyline, but for some reason, now you don't want to delete it and assign it again if you want to just stretch something or move a vertex. So notice this catchment area label and notice the area here in the data table. I will just here pick on this vertex and I will say add a vertex. And I will, for example, move it here and notice how everything is dynamic. We see that the label automatically refreshed and the data table as well. So you can move it. You can even remove a vertex and everything will work automatically and dynamically. Also, if we want to edit the catchment areas, let's select all of them. You see that you can rename them using the data table because the cells are white, or we can go to Canalis panel, area editor, and you have many options for editing of the catchment areas. You can rename them. You can rename them automatically. You see that the dialog looks just like the dialog that we used on the first session for renaming of the sections and for the nodes. You can use, for example, branch or array name. So this is a nice option because some users like to use, for example, starting node of the first section that is assigned to that area as a name for that catchment area. So you can just take it. For example, I will remove this A, which is prefix, and I will type just monkey1, and you can see this is the old name, this is the new name. We didn't apply it yet. And monkey5 is for counter. So this is the prefix of a branch name. Or let's say what is monkey2, this is array name, or first section name, or first node name. So this is nice option. Or you can just put some prefix like this and it will be like that. I like this, for example, the name of the array, name of the channel, like this. And for the delimiter, I will put the point and I will just click on apply. And now all my areas are renamed so that are having this pattern. So channel name as the prefix, and then I have some suffix as well. Okay, so these are the renaming options. You also can delete the areas from here. You can hatch them with the permanent hatching. You can remove the label or label them with some other label from the catalog. You can also change some of the parameters, change the type of the area. You can set which sections belong to catchment area. This is a really nice option. For example, if you want to, let's select, for example, this one, you have all the sections that belong to that catchment area. And for example, if you want to change this selection, you can select, for example, just parts, just some of those sections and click apply. So you don't have to delete everything and draw it again just for the editing purposes. Okay, so this is it for the catchment areas. We will save this drawing and we will switch to the drawing that we basically designed ourselves during this training. So let's call this final and let's close it. And I will open the drawing, this following one. I have it here, flow calculations. Let's open it. Okay, so this is basically, you remember, this is the very same file that we draw yesterday and the day before. You can see that we have our configurations here. We have everything, our styling, our theme maps, our configurations for profiles, configurations for manhole schemes, everything is here. And we designed this system, but also what I put here, I put these polylines that we will convert to catchment areas, and also one polyline that we will convert to industry area as well. This time we will create both catchment areas with the for the rainfall, and also we will create influence areas from the same polylines for the sanitary calculation of sanitary sewage water. Okay, so to do this, first of all, let's create the catchment areas. But now, like I said, these are polylines, so we can use the other option for creation. So let's do it. Let's go to Canalis panel. Let's go to area definition. And this time you see by the polylines that we will use the option for selection of the arrays. Okay, and I will say for this entire array like this, let's define the object. So if I'm not using the point selection, I don't have to use layer filtering. So just select a polyline like this. And let's now define the data. I can immediately say that this is both catchment area and house influence area, but also I can do it later. Like I showed you, I can edit it and I will later put it that it is also a house influence area. So it says here that I have for the rainfall runoff coefficient of 0.75. So I can just type it here, 0.75, or again, I can use one of these soil types from the catalog. I will use this mixed, which I know that we defined to be 0.75. Let's click apply, and now you can see that this is applied. Let's click save. Let's continue. Let's say for this one here, let's select object. Object is this polyline. It will be mixed, so I don't have to apply anything. Just click save. Let's go further. For this one here, let's select an object. It will be this one here. Again, mixed 0.75. Let's click save. Let's close this and we can check it. Again, we have this default color of the layers, which are predefined for work on a black background, so we can change it. But like I said, if you want to change something about Urbano layers, go to your system, edit, find that layer in the list of layers. This is it, catchment areas, and I will put some darker color, let's say this 150 blue, and this also I will put 150 blue. Let's click OK, and now we can see that we have these labels here, and the label is with the name, area in hectares, and runoff coefficient. Okay, so that is it. This one we will create later. And now let's talk about flow calculation. In Urbano, we have multiple methods for flow calculation. We have some pretty basic ones, and also we have some pretty, we can say complex, not complicated, but complex ones. And also we support many different country standards. For example, because we are doing this software for many regions from, I don't know, Germany to Turkey and Bulgaria and practically all this Central and Eastern Europe. You will see that when you open this this dialog for flow calculation, we will have a lot of different methods here. So for example, you have this extension, this suffix RO, which stands for Romania. You have some of this which stands for Bulgaria. Also, you have some for Turkey, for Germany, and stuff like that. So, and of course, you can turn them off so you don't see it. But if you install the English language version, you will have all of them. So how to turn them off? I like to turn off this very country-specific calculations. So I will show you, but before that, I will save this file and I will call it, let's call it immediately final, save, and let's close Urbano. Let's close Urbano completely. We already saved this, but okay. So everything about this flow calculation methods are saved in this file, which is called flow calculation registry.xml. So I will send you with today's files. I will also send you this XML file because you can just copy it. You can go to your installation folder. You can also turn this off manually, but it's better that you just use this file that I sent to you. So you have to go again to C, Program File Studio Ars. Let's go to the folder that I'm using, this one here, language of the version, year of the version, and just paste it here. So paste it, replace the file in destination, and now you will have this flow calculation registry with just the basic methods. You will not see all these country specific options because there is a lot of them and it will be easier for you, especially as a beginner user. Okay, let's now open Urbano again, and you will see that when we open this flow calculation dialog, that now we will not see this Romanian, Bulgarian, and other methods because I turned them off in this XML file. Okay, so we will open this file now that we left off. This is the flow calculation final that we saved. We have to wait a few seconds for all of the Urbano functions to load inside of the Civil 3D. That's it. And now I will open again this flow calculation final, and that's it. And now if we go to our flow calculation, you will see that we have less methods here and it is much more easier to use. So we now don't see the Bulgarian and Romanian and other methods. So first of all, we'll talk about this simple rational method where you basically have a runoff coefficient, rainfall intensity, and area of the catchment that belongs to each section. So to do it, you see that you have many different methods. So to create a calculation, you have to click on a method and click on add. Okay, so this is called rainfall. This is called simple calculation. Basically, it is a rational method, CIA method. So basically, you have, like I said, a runoff coefficient. You have a rainfall intensity, which is constant. You define rainfall intensity here, and basically area of the catchment area that belongs to each section. Also, you can define some additional coefficients like reduction coefficient and retardation coefficient. Also, this simple method can be this, as we call it, common method, or ATV method. This is German method. And also I will send you this this PDF file. It is from older version of Urbano, but it doesn't matter. The formulas don't change. So if we go to find this retardation factor and the other one, you can see it here. It's used for simple method, and this is how it is calculated. So reduction coefficient and retardation coefficient, you can calculate them by these formulas if you want to include it, and you have to define, as it says here, this factor n. And also for the ATV method, if we click here on ATV and search, you can define this ATV frequency n and ATV raining time n. So it's specific methods, so even I don't know this by heart. I have to check it. And if you want to assign these coefficients, of course, we can just click here, right, and these coefficients will not be taken into account. So we have runoff coefficient multiplied with constant rainfall intensity and catchment area, and you have the rain flow for each section. But let's reset this. Let's go to coefficients, And here we have this factor n. So if we include it, we can define it, but it says here that some default value is 6. Okay. And if we now just select everything, save and close, now you can see that the reduction coefficient has been automatically calculated, and the retardation coefficient is always 1, because it says here that if the area is smaller than something, it will be in cases when the catchment area is smaller than 1, the coefficient of retardation is recommended to be 1. So that's how it works. And now if we just click on write, everything will be calculated, and we see that these coefficients have been taken into account, and we have some different values than before. So these are the simple calculation, like I said, which can be common method or ATV method that use these coefficients. So you see factor n, or for ATV you have ATV frequency and ATV raining time. Okay. Also, we have more complex IDF method, which I will show you later. So these are the rainfall methods, and we calculated just the flows for each section, but now we have to calculate the total flows because you have the transit flows. So to do this, you have to go here to the scenarios, and you can create a new scenario, as we call them. And I will give it here a name. I will call it simple method, like this. Okay, so runoff coefficient, rainfall intensity, area of the surface. And all you have to do, just click on write, and based on this, you see, based on this calculated data for each section, the software is automatically calculating transit flows through that section and total flows. And we can see that the maximum total flow for the entire system is a little bit less than 415 liters per second. Okay, so these are the rain methods. Later on, we will talk also about IDF method, where the rainfall intensity is not constant, but it's taken from the IDF curves. So let's now talk about waste flow. First of all, we have percent calculation. So I will show you what that is. Just add a new configuration. And here you can define what is the consumption of water per inhabitant per 1 day in liters per day per 1 inhabitant. You can define number of people. You can define annual population increase during the design period, and also coefficient of variation per day, coefficient of variation per hour, and reduction coefficient. Because this is basically calculation for the usage of the water, but it doesn't have to be that all of the water supplied to the user will end up in the sewage system. So you can use reduction coefficient. I will use it 0.9. Okay, and so based on this data, based on this annual population decrease and this design period, let's check it here again. So design period, this is the formula how the number of the inhabitants, ending number of inhabitants is calculated based on this data that we supplied, because we supplied the starting number of inhabitants, annual population increase during the design period. So now if we check what the software calculated, by multiplying the consumption of water per inhabitant with the actual ending number of inhabitant, it reached that we see that the planned number of inhabitant is this value here, so 9,056. The software calculated average demand per year in liters per day. That value is multiplied with the coefficients of variation per day and per hour, because we have to know the maximum hourly demand. So that's how we get the maximum demand per hour in liters per second. And then we have the total length of the entire system, and we calculate specific demand. So this is liters per second per 1 meter of the system. And this is the number here. And now when you click on write, this number is multiplied with each section's length, and you get for each section the waste flow. Again, this is just for each section, so we have to calculate the transit and total flows. Again, let's create another configuration, another scenario, and I will call this percent calculation, like this. And we will turn off simple calculation, so we will have only percent calculation. Again, right? So you can have any amount of these scenarios, any amount of these configurations, and you can create your own calculation methods. Of course, if this is a training, when you are working with a real project, you will use only one method, but we are here to show you all the methods. And here we see that this is the total flows for this system. Also, just like before, you can use some coefficients. So let's also show this. I will create here a new, you can also have different configurations for the same method, no problem. And I will call this virtual lengths. So what are virtual lengths? You see here that you have total length of the sections and total corrected length of the section. What is this? So we can again go to coefficients, and for this method, you can use this population density coefficient. Here in the description, it says that this is coefficients used for waste flow by percentage calculation. So it's each calculation, it is for some of the methods. So how this works, we can virtually increase or decrease lengths of some sections, and by doing this we can say, okay, this area is here we have more people concentrated, more of the flow will be here, and on some areas we have less flow. So you can select this array, for example, or any part, and I will say here we have population density coefficient 2, save data, okay, and here I will say 0.5. okay, let's click save. That is it. Here I will leave 1. So if it's 1, you don't have to set it because the default is 1. So I will leave the number of people the same, 5,000, all the data will be the same, reduction coefficient will be 0.9. Okay, and when I click right, you can see now that the specific flow is different. And why is that? Because we have the same maximum demand per hour in liters per second, but now total, you see here, section length is multiplied with the population density coefficient, and these are the corrected section lengths multiplied with the coefficient, and this is what we call virtual section length, and total corrected length or virtual length is now bigger. So the same number divided with the larger number, we have smaller specific flow. So we have smaller specific flow, which is now multiplied again with each section's length. Okay, let's click here on the group so we can compare these two configurations. And for example, now if we select this array, we can see that for the virtual lengths, because the population density coefficient is bigger, we have bigger values. And if we click, of course, on this one here, we will have smaller values. But also, if we click here, we also have smaller values because we get the smaller specific flow. So that is how this virtual lengths work. But of course, when we calculate the total flow, total maximum flow will be identical to this percent calculation. It's just a matter of different distribution of these flows. Okay, I don't need this, so I will just delete it, and we will have just this percent calculation. Okay, also, so this is the let's say simple way to calculate sanitary flows, but also we can use this, like I said, influence areas. So first of all, we have to create influence areas, and these influence areas can be for house wastewater flow and industrial wastewater flow. So let's do it. I will close this. let's go back to area definition, or let's go to area preview first, because we already have these catchment areas. We will just edit the parameters. Like I said, we can go to area editor, or you can edit them in this preview. So I will select all three of them by pressing Control button. Let's go here to set parameters, and I will set type to be also house influence areas. And for the population, I will say 1,000 people, because it's how I have here, 1,000 people, 1,000 inhabitants per 1 hectare of the area. Let's click OK. And now you see that we have 3 catchment areas and also 3 house influence areas. And now the area type, we see that is also the catchment and the house. And now the density is 1,000 inhabitants per hectare. Okay, that's it. And let's also create this to be industry area. Let's go to function for area definition. Now, of course, it would make much more sense if we design one more branch for this connection and then connect it here, but we know how to do it, so we will not make this more complicated. I will just say that, okay, for this section here, we will say that this area will go directly into this section of the main channel. I will select an object, this object here. Okay, and I will turn off, it's not an catchment area, it's only industrial influence area. And for the label, I will not use label for the catchment, but label for the industry. Let's click apply. Okay, we see that the soil type and runoff coefficient is not defined, and the density, because it's just the industry area. Of course, it can be both industry and house and catchment, no problem. Let's click save, and this is created. So this is the name, and this is the area in hectares. Okay, let's now go back to our flow calculation, and let's go to house wastewater flow. Let's create another configuration, and basically how this works. So now each section has its own house influence areas. Again, the very same calculation as before, it's dependent on each section length, it's calculated proportionally. We now know population density, number of inhabitants per hectare, and if we multiply these two numbers, we will have number of inhabitants living on each section. And now here we have this wastewater flow coefficient, which is in liters per second per 1,000 inhabitants. So I will put 7, for example, and we have 7 liters per second, which is divided by 1,000 and multiplied with the actual number of inhabitants on the section. So just click on write, and this is it. So the number that you input here divided by 1,000, because this is for 1,000 inhabitants and we only have 60. So this is how we calculated house waste flow for each section. Let's do it also for the industrial waste flow. Let's create another configuration. And here we have industrial influence area. You see everything is not defined except for this section, this one section here. Okay, and wastewater flow in liters per second per acre, and we see here that it is 30 liters per second per acre. Okay, hectare, pardon. So 30. Okay, let's click write. Okay, and now you can see that the resulting flow in liters per second for this section for industry waste flow will be 5 liters per second. This is just for those sections. So again, we have to go to scenario. This is basically calculation of total flows, and you can use any of the combination of previously defined method. So let's call this influence areas. Okay, and I will turn off simple, I will turn off percent. We will have only house and industrial. Okay, let's click write. That's it. And now we have again total section own flow. So this is now, for example, for this section, it's this plus this is this. We have transit flows. So this is the flow, all the flows that go to that section from the whole system before, and this is the total flows. Okay, so these are the methods for the waste flow. Let's also check some of this. This is the additional flows. So even if some of these methods is not up to your wishes, you can also define point flows. So just create a configuration of point flow, select sections. For example, I will select this one, and this one, and quantity, let's put 10 liters per second. Let's click write, and it will be exactly 10 liters per second. Or let's click on reset. You can go using data table and type 5, enter, 15, enter, 10, enter. So basically you can define flows even in this way. Also, you can import flows. For example, if you calculated your flows manually, you have them in Excel, you can import them through Excel file, text file, any format that you prefer to use. So this is the point flow. And also, if we click here on point flow again, I will add another configuration. I will call this now outflow. So these point flows can be positive values, but also they can be negative values. So here you see the point flow can be inflow to section starting node, or it can be outflow from starting node. Okay, this is really nice functionality. So I will select, for example, here, let's say that here we have some outflow, some overflow if the rain is too big. Let's select this section, and it says from the start node of the selected section. And here I will say 90. Okay, let's click write, and you see that the value is minus 90 because it is outflow. Don't define minus 90 because right, it will be 90. So you define the positive value, right? Or if you are using the data table, you can just type minus 90 or minus the value. Okay, so this is the point flows. Let's also check this additional rainflow and foreign waters. So if we add new configuration, so this is basically like it says here, additional rainflow inside wastewater channel. So if you have some cracks on your old pipes, you can even using this way basically calculate the inflow of rainflow into your wastewater channel by using this coefficient. So it says additional flow coefficients in liter per second per hectare of the area. So default is 0.2. Let's click write. So basically 0.2 multiplied with this, you have also some kind of additional rainflow. And of course, you can create a scenario and include any combination of these above methods. And also foreign waters. This is something to basically include some, we can say some illegal connections, for example, because we always have some design flow, but for some reasons we also want to be on a safe side and increase that flow a little bit because of, we call this foreign waters, unknown waters, or whatever you want to call them. And basically this is again just some coefficients. You can use house wastewater flow influence areas. So this is the method only, this one here. We have two methods. This is if you are using your house waste flow influence areas. So how is this working? You can use this coefficient, as you see, in liters per second per hectare or liters per second per inhabitant. If this coefficient is turned on, if this checkbox is turned on, it says population density, then it is liters per second per inhabitant. And again, we have here number of inhabitants. So on each section, I will type, let's say 0.01, right? Which is now multiplied with this, and you get this foreign waters. Or if this is turned off, then you define liters per second per hectare of the house influence area. So let's put maybe 1, right? So this will now be this. So coefficient multiplied with house influence area. It's really simple. But maybe the more interesting option is this: specific flow for foreign waters, and coefficients is in liters per second per 1 meter of the section. So if this is section length, by each meter we include some, let's say, foreign waters. So if we click right, this is it. Okay, so these are all the methods for flow calculation. I really hope that you find here something that you like. And like I said, if it's just not for you, of course, you can import, let's say, from Excel. So that is it. And now at this point, I would like to save this file. I will call it, okay, final. But I will also do this. I will save this as, we'll call it final 2. Okay, why? Because I would like to now do something that is not just for the showing, for the training purposes. Let's do something that you might want to do in your real project. Okay, so obviously we will not have both percent calculation and house industrial. We will have only one method. So let's delete this percent calculation. We will leave only this. Only this, also this point flow, I don't need point flow, I will delete it. Outflow, I will leave. Foreign waters, let's delete it. Additional rainflow, let's delete it. Let's say that we have, and also these scenarios, I will delete all of them. I will send you both files so you will have all this. But now just to make this more simple, let's say we have rainflow calculated by simple calculation. We have influence areas flow, and we have some outflow. Okay, let's now create real scenarios. Let's call this, I will call it dry period. Okay, and here I will have only house and industrial waste flow. Let's click right, and we see that the total flow is 38. Okay, let's go on and create another, or we can copy this one. Just copy, it's easier. Okay, just rename it, and I will call it wet. And of course, not the results will be copied, just these checkboxes. And for the wet period, I will include also the simple calculation, also the rain. Let's click right. Okay, now the maximum is 453. Let's create another one. Again, I will copy the wet period, and I will call this wet period with outflow or overflow. Okay, so basically now I will include everything. Let's click right, and that's it. We have the total flow, which is now smaller, because if we go here to selection of the sections, let's select this one, and this one. And now if we check the total flows in this section here, we have 103.79. From here we have 110.14. And if you sum up this, so let's just open the calculator. If we sum up here 103.79 plus 110.14, you will get this 213.94. Okay, this is because of the rounding of the decimal places. And now this is the transit flow. So what comes in here and here is the transit flow of this section, and this is it. And now in this section we have, from the simple calculation, 948, for the house flow 0.76, and the outflow of -90. So if we include that as well, so plus 948 plus 0.76 minus 90, this is the resulting flow of 134.17, okay, 18. So that's how you can use this outflow to basically reduce your diameters and total flows. Okay, so now we have 3 scenarios, and what we can do, basically we can go to scenario preview. And what is this? This is basically parallel hydraulic calculation. Let's check options. And one more thing, it's important to say that all these methods that we calculated here, it's not important for this method. This is we can call them 2D methods for calculation of the flows. You don't have to have invert elevations defined to calculate this. Also, you don't have to have the pipe diameters defined. So it's not important for these methods. For the IDF method that we will cover next, you have to have the invert elevations already set. This is why this method is different. But also, we yesterday defined the pipes here. Just randomly, I was showing you the function for setting the pipes. But now we will do real pipe sizing. Of course, I can just run the pipe sizing and the pipes will change, but I would like to delete them so that we have nothing. Let's just select everything and delete data. Okay, so you see that there is no pipes anymore. We resetted the pipes. You see how the style automatically updated as well. Okay, let's now go back to our flow calculation. Let's go to scenario preview and let's go to options. So hydraulic calculation type, we can calculate to existing data, existing diameter and slope, but we do not have the diameter because I just deleted it. And I will say pipe sizing. So let's do pipe sizing. We have to select a pipe group from the catalog. I will use, let's say, this PEHD pipes. Okay, now for the fulfillment of the pipes, we can have fixed percentage, let's say for all pipe diameters, fixed is 80, or we can say percentage by pipe diameter. And here you have this list of pipe diameters. So up to this diameter will be this allowed filling percent, up to this diameter it will be this allowed filling percent. I don't change this, but you can if you want. Okay, and minimum pipe diameter allowed, let's say 300, okay, millimeters. Okay, and now let's select this scenario, this scenario, this scenario. And basically the software is doing parallel hydraulic calculation, and here we can compare with different colors, dry period, wet period with the outflow. We see flows, resulting nominal diameters, filling heights, filling percentages, velocities, and flow times through section. Of course, you can also select just parts of the area, part of the system. Let's say, let's select just this main channel. And now we can compare it. And of course, we see that the dry period is requiring the smallest pipes. The wet period is requiring the biggest pipes, as you can see here. And this wet period with the outflow, it requires some, let's say, modified pipes. Also, you can compare this by, if you pick on this icon here, you can have all results for 1 scenario, 2 scenario, 3 scenario, or I prefer it to alternate data like this, data by data, and compare everything. Also, like any other Urbano data table, you can select everything, you can sort it, you can select everything, you can copy it, we can go to Excel, and here we can paste it, and this is one way how you can paste it without these colors, like this, or you can copy it as HTML. This is really nice. So now when you paste it, you have also this really nice color. So this is basically, if you need these types of calculations, this is something that you can straight put in your project, and basically you have it for 3 different flow scenarios. Okay, let's now go back here, and this is just analysis. We still didn't apply anything to the drawing. So now if we want to run hydraulic calculation and save the results, we have to go to this hydraulic calculation. Again, everything is the same as in the function before. All these parameters are remembered. So now you just have to select what is the flow scenario. You can have sum of all defined flows, which is basically the same in this case as a wet period with outflow, or you can select one of the scenario. I want to size my network according to this scenario, wet period with the outflow. Okay, let's calculate. You can analyze it before saving, but we already did this. We see all these values here, like total flows, full pipe flow, flow percent, filling height, inner diameter, filling percent, velocity, full pipe velocity, velocity percent, flow time, and stuff like that. And you can save it. Okay, and now you can see how everything automatically updated, the labels updated, the pipes updated, the profiles updated. We can check here. Now you also have this I will just redraw the profiles with redraw icon for this to update. You also have this really nice option of showing the levels, water levels in the profile for this flow. Okay, so let's also analyze this a little bit through the labels. So if you want to put hydraulic values in the labels, of course you can do it. Let's run this label with the data for diameter, flow, and velocity. Double click on it, select everything, apply it, and now we have it for each section: diameter, flow, and velocity. Also, now we can use team maps and also queries. Now we have more data, and now the team maps and queries start to begin much more interesting. So for the team map, let's apply velocity team map. Double click on it, select everything. Let's set the legend position, and let's put it here. And now we have in different colors, we have places where we have really high velocities. It is from 4 to 8. So maybe we would have to react here and maybe input more of these drop manholes, because you see that the flows are not that big, but the terrain is very steep. So that's why the velocities are really high here. So we can see they go up to 7 meters per second. Okay, but that's how we calculate it here. That's how we set up this invert position to be really high terrain slope and also invert slope. Also, we can analyze it through data tables. So we have here also the special configuration for the section hydraulics, where you can check all this data about the hydraulic data. And also we can sort it. Let's sort it, for example, by velocities. And we can see where we have this high velocities. We can mark in plan, and you can see that this is here, this steep vertical sections. Also, one really nice way how to analyze through data previews. We can go here to section hydraulics. We can edit these previews. And for any data, I will do it for this velocity data, we can turn on this validation data here. And I will say validation type is between minimum value, let's say 0.40, and maximum value 5. This is not any kind of error detection or anything, but it is just a visual for you, visual warning for you, that now you can see that the velocities that are, in this case, we have no smaller than 1.10, But for example, if we have only dry period, we would have small velocities, but we have this wet period, so we do not have small velocities, but we have these high velocities because of these really high slopes that we defined here. Okay, so this is it from this this example. Let's save it. And now I will show you also the IDF method. This is the rational method, also CIA method, but using the variable rainfall intensity, which is read from the IDF curves. So the IDF curves, as I have them here, are basically text files, plain text files. The format can be .dat or .text. So basically just plain text files, which you can open and edit with the notepad. And this is the format that you have to have. So hashtag with the return period, frequency of the rain. You have the, in minutes, the duration, the concentration times of the rain, and the intensity of the rain for that time and for that return period. Of course, the higher the return period is, the higher the rainfall intensity is as well. And that's how you create the IDF curve for Urbano. Okay, let's now go to this system. As you can see, again, the very same drawing that I used before, but this is now the real project done by the users. And you can see that if I go to the preview for the catchment areas, that all the catchment areas are defined, but you can see how this user defined the catchment areas. Not like I did it before, but the users define that each catchment area is defined for one section. So one section, in this case, this is one storm drain, is one catchment area is defined for one storm drain. So it's also possibility to do it like this, but it requires a little bit more time to do it. Okay, so let's now show this IDF curve. If we go to profile, we see that we have only pipe invert, and also we can see here also in the plan as well, and also we see in the label as well. So let's go here to Canalis, let's go to flow calculation, and let's go to rational IDF method. So this is a little bit more complex method, but it's also a really nice method because it is cumulative. It automatically calculates the total flows, and also it automatically can size your network. So it doesn't require you to first calculate flows for each section, then calculate total flows, then go to hydraulic sizing, pipe sizing. You can all do it with just one click. So let's create configuration. Okay. You have to select IDF curve, IDF file. So let's do it. You can select either dot or text files, the same. Okay. Now you select frequency, which is return period. Let's put, for example, 2-year return period. Okay. You can ignore pipes without its own catchment areas. This is the characteristic for this method, but it's irrelevant here because we defined for each pipe its own catchment area, so it will not make any change, but you can use it. And also, this is really nice option. This is basically what I said before. If this is turned off, it will only calculate you flows, but if you pick this option, then it will automatically size your network as well based on that calculated flow. This is the cumulative method. It is also automatically sizing the network, so you have to set these parameters. So for the pipe group, let's use again this PEHD pipes, okay? And you have to define these sizing options. So again, I will use percentage by pipe diameter with the list of these filling percentages, and the minimum pipe diameter I will use 300. And now, because this option, I will just click on write. Okay, it says inflow time was not set. So this is really nice. If you miss something out, the software will notify you that something is missing. Okay, and let's now go to coefficients, inflow time. And it says here that the rainfall inflow time has to be set for IDF method, which we are using now. Usually it's 5 minutes or 10 minutes or 15 minutes. We will use 5 minutes. Let's click save like this. Let's go back to preview. Let's write it. And now everything is calculated. So how is this calculated? You have catchment area for each section. You have runoff coefficient. The software is multiplying these two values and it's calculated corrected catchment area. Now, like I said, this method is cumulative. So it's cumulatively calculating the sum of corrected catchment areas. So this plus this is this, this plus this plus this is this, and so on and so on. Now we have inflow time that we defined. We have flow time, which is calculated. So inflow time is the time which one raindrop needs to come inside of the system. And then we also have flow time through the system. Reference flow time is the, again, cumulative time. As you can see, it is increasing. Concentration time is basically a reference flow time plus the inflow time. And based on this concentration time, the software is going to IDF curve. And for that concentration time, it reads the matching rainfall intensity. So you now see that the rainfall intensity, unlike the simple method, is not constant. It is dependent on the concentration time. Based on the slope, that's why I said for this method, you have to have slope. The software calculated all the diameters and the flows. Okay, so let's close now this, and you can see, okay, this is overlapping, so just refresh the labels, go to labels, refresh the labels, and now you see that we have the pipe diameters. We have also here the labels, everything automatically refreshed. If we go to the profiles, also you can refresh the profiles because these trenches will also appear because they have been predefined from before. And also we see that we do not have this water level, and this is just the styling of the profile configuration. So if you want to include it as well, you go to edit of this configuration. You have to select the pipe like this and filling level, including drawing. Okay, that's it. And now also for these pipes, you have the filling level of the water. And also you can see that the data about the hydraulic calculation like flow, velocities, filling heights, everything can also be here in the profile data table as well. Okay, so this is one way. This is one way how you can use IDF method. Let's save this. Let's save this to, I will say, final one. Okay, let's save it. And also let's now again reset these pipes. Let's go to pipes. Let's reset it, all the pipes. Let's delete it. Okay, we have no more pipes. Let's go back to flow calculation. Okay, let's reset the results. Okay, and now I will turn off this option for writing the pipes and calculation results, meaning the automatic sizing. Let's turn this off. Okay, even though to calculate flows, the software will do the sizing, but it will just calculate you the flows. It will not automatically save the pipes to the drawing, because you can combine it. Again, you can just calculate the flows with this method and then also calculate the waste flows, and then you can calculate again the total flows and use this for pipe sizing. But also what can we do here? So I will call this, instead of just rational method, I will call it return period equals, for example, 2 years. Okay, and frequency will be 2. Just click right. And now you see that it calculated the flows. The flows are the same, but it didn't automatically size the network. Let's copy this configuration. So everything will stay the same, but I will call this configuration return period is 5 and frequency will be 5. Let's just write this as well. Let's now go to these scenarios and let's create two scenarios. One, I will call it return period equals 2 years. Okay. And the second one, I will call this return period equals 5 years. Okay, that is it. For the 2 years, I will turn off 5 years, of course, and click write. For the 5 years, I will turn off 2 years and just click write. And again, we have two different scenarios. So one for the 2-year period and one for the 5-year period. Now we can again go to scenario preview. We can go to options. We will do again sizing, not according to existing data, but pipe sizing, because I resetted the pipe. The pipe group, let's use PEHD pipes again. Let's use again this percentage by pipe diameter and minimum pipe diameter 300. Let's click OK. Let's turn on this. And now again, we see that the software is doing parallel hydraulic calculation. And we can see that for the yellow scenario, for 5 years return period, it's required the bigger pipe in the last section. So if we close this, nothing is automatically done. It's just for analysis. And if you want to do it, go to hydraulic calculation, select the scenario. All this is remembered from before, calculate it, save it, and we can close it. Now you can see that everything is sized. Okay. We see that, okay, it didn't automatically refresh correctly. So you can pick here on the reindex button. So if you see that something is graphically not right, you can click here for the plan view. You can click on the labels, refresh for the labels, or for the profile, redraw for the profiles. And that's it. That's basically the IDF method. Okay, let's now save this. I will save this as the final tool. And now I would like to show you one workflow, how to work with the, let's go to pipe sizing. Okay. I will show you how to work, how to optimize the pipe diameters and also how to optimize the pipe inverts as well. So here we have one system. Let's check it a little bit. So let's switch again to catchment areas. We can see that we have some catchment areas defined for the multiple sections, majority of them assigned only to one sections. And we see that these are all basically simultaneously both the catchment and house areas. And also we see defined runoff coefficients and population density in number of people per hectare. If we go to selection, we can also see this data, these catchment areas as well. We can select it, we can preview it, and everything that we showed already. Okay, let's now draw profiles. I will draw profiles using this configuration. Let's place them one below the other or in group, doesn't matter. Let's draw them here for all these arrays at once. And we can see that we have terrain elevations defined, but we have no invert elevation set. Let's open the data tables. Let's switch to section geometry. Let's select the whole system, and we see that we have no values for the invert. To do it, I will use again automatic invert calculation, and I will run this first configuration. I defined minimum and maximum depth below terrain, minimum and maximum slope as a constant values, 1 and 70, because we have to start from somewhere. This will be first iteration of this process. Okay, and I will say for the whole system, calculate, and we can preview it. and we can apply it. Okay, so we have the first iteration of this inverts. Okay, let's now define the flows. Let's go to Canalis panel. Let's go to flow calculation. Let's create one simple calculation. And for the rainfall intensity, I will type 96 constant rainfall intensity. Let's click right. Okay, for the waste flow, I will use house waste flow because we have the influence areas already defined. And I will say coefficient is 3.7 liters per second per 1,000 inhabitants. Let's click right. Okay, that's basically it, but we can create also one scenario, and let's call it wet period. Okay, like this, and we will include everything. So it will be both storm and sanitary. Let's click right. Okay, and also let's create another scenario, just dry period. Okay, and here we will have only house wastewater flow. Okay, so we have two scenarios. One is just for the dry period, one is everything for the wet period. We have really high flow, as you can see here. So now let's go to hydraulic calculation. Okay, we will again use we'll use wet period for pipe sizing. So let's go to pipe sizing. And now for the pipe group, let's also use these PEHD pipes. Okay, we will use the percentage by pipe diameter and minimum pipe diameter 300. And notice this now, when I click calculate, it will say that the flow is greater than the maximum for defined pipe, which means that in my pipe catalog, let's check it, catalog of pipes, PEHD pipes, the maximum pipe is 600, which is not enough for the very large flows that we have here. So now I will show you how to create your own catalog, how to create your own pipe catalog. We will create a new group and I will call it my PEHD pipes. Okay, now I can add a new, I will use circular pipes like this, and I can enter all these values one by one, but I prefer to import it from Excel. So I will just keep adding this. I will add 10 pipes, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Let's now edit this group data. I will pick here and I will copy this. So this is the template. You have to enter in this template. So let's copy and let's go to Excel. Here I have this PEHD pipes in Excel. This is, let's say, my catalog, and I here have some data. I will paste this template from Urbano that I have to fill. So let's copy the names here to names. Let's copy pipe material and pipe roughness here. For the pipe manufacturer, let's say I will type something. You don't have to, but if you have your some local manufacturer, you can also type that. Pipe description as well. You can put anything. Also some other stuff as well, but I don't have it. So I will use inner diameter, nominal diameter, outer diameter, wall thickness. Let's copy and let's paste it here. Okay. Minimum and maximum slope. For each pipe diameter, you can set it. You can set it, or I calculated it. So in Croatia, we do it like this. Also, I know that in Turkey, they do it like this. So I'll show you how I calculated this, and then you can check, okay, this is for me or it's not for you. So I will copy this and I will paste it here. So how we calculate this? It's in relation to inner pipe diameter. So we do it like this. We say it's 1 divided by the inner pipe diameter and multiplied by 1000 to get the to get the per miles. Okay, and that's it. So let's just do it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 for all pipes. So this is the minimum slope. And for the maximum slope, we do it like this. So it is 1 divided again by the diameter, but now not in millimeters, but in centimeters. So we do it like this. We divide this by 10 and then also multiply it by 1000 to get the per miles. So basically it's always 10 times higher. So you can do it like this, or I don't know, you can just manually enter for each pipe, you can enter minimum and maximum slope. And this will help you out for the sizing and optimization of the pipe invert. And also you can have some custom data. I don't know, some description. I can put it in the description, or I can put it for each pipe. You have custom data 1, custom data 2, custom data 3. You can fill anything here and you can use that data everywhere in the data tables, in the profiles, everywhere. So I will paste this here. And now I have my catalog. So I will take all this, I will copy it. Okay, let's go back to Urbano. Here, pick in the first cell and just click paste. And that's it. We have our own catalog up to 1200 millimeters of the pipe. Let's click apply. Let's click OK. And our pipe catalog is now completely defined, and we can continue with our hydraulic pipe sizing. Let's click OK. Be sure when you edit something in the catalog to click OK. If you click cancel, nothing will be saved. If you exit with escape or with this X, nothing will be saved. And it's without warning, so be sure to, when you want to save something, to click OK. Okay, now we can go back to hydraulic calculation, and let's now switch the pipe group to my PEHD pipes. Okay, and we will click on calculate. We will click on save. So now that we have the diameters as well calculated, we can repeat the procedure of automatic invert calculation. So now I will go to this second configuration that I called next. Everything is the same, but now minimum slope is read from pipe catalog and maximum slope as well, based on the resulting diameter. So let's select everything. Let's calculate. Let's hide this dialog to check it. And now we can see how the software is now changing the pipe inverts. Okay, let's apply this. Of course, everything changed. And you see that when something is changed in Urbano or newly calculated, it is in blue color. So we have everything is now different. Of course, now we have to rerun our hydraulic calculation. So let's go to iteration number 2. Let's go to hydraulic calculation. Let's again calculate it, and we can check it. Let's check the diameters. So some diameters are black, which means they remain the same, but some are blue, which means that they changed. It's higher or smaller. So let's click in front of the these brackets, you see the old value, and inside of the brackets are the new values. So when you click save, the new value is saved. Okay, so we see that we have some new diameters, so another iteration is needed. Let's go again to next configuration, calculate everything. We can preview it or we can just apply it. Okay, let's save it. We see some of the invert elevations changed. Let's now go to the final iteration. Let's go to hydraulic calculation. Let's calculate it. And now you will see that all the diameters stayed the same, which is now 2 iterations are completely the same. We do not have to go to the next iteration of the pipe optimization. And that's it. Let's save it. And we have our final results for the pipe inverts and for the pipe sizes. And now we can go even to our scenario analysis. Let's go to flow calculation. Let's go to scenario analysis. But now if we go to option, we do not have to go to the pipe sizing anymore. Let's just check according to existing data and slope what will be. So we size our network, but let's check, okay, what will be the velocities when there is no rain? What will be the pipe fillings? So we will go to according to existing data, okay, like this, and let's click OK. And now you will see that the diameter is not part of the scenario anymore. The diameter is not in color, and we just, for the fixed pipes, we compare flows. You can see how the flows during the wet period are much bigger. We see the filling heights, filling percentages, we see the velocities, we see the flow times. Okay, so I will save this drawing as well. Let's go to File, Save As, Pipe Sizing Final. And now for the final topic today, we will talk about hydraulic calculation and pipe sizing of the pressure pipelines in the sewage network. So in Urbano, you can have a mixed type of the system. There is no problem. You can have parts of the gravity system, parts of the pressure system, but you have to know just to run different calculation methods, different dialogues. For this is for gravity network, and this is for pressure pipelines. So let's check this system a little bit. This is also a real project done by Urbano users here in Croatia. So you see that the user applied different styles. We talked about different styles during the first session. So basically you can use these styles not just to apply different visual style to entire network. You can create a different visual styles to separate, to differentiate your parts of the network. You can have, for example, blue style with different smaller nodes, node blocks for the pressure pipeline, and different blocks and different colors for the gravity network. Again, we see some custom blocks, custom labels. We see the station labels that we talk about today. And also, we can also go to our data previews. We can go to data previews here. And also we can see one data here, system type. Is it a gravity or is it a pressure? And how to set this parameter. You go to edit system type. And it is important to say that when you start drawing in Urbano, by default, everything is gravity. So you only have to select parts of the system that you know. Of course, you cannot know this when you start your project, but when you draw the profiles, when you draw the pipe inverse, when you see that somewhere you are going too deep, you can say, okay, from here to here we have pressure pipeline, and you go to this function and you define what are the pressure parts. But it is strongly recommended, you can define that the pressure part is from node to node or sections, but I strongly recommend it that one pressure pipeline is one branch. So you can see that that's how I defined it. Each this blue branch is one pressure pipeline. This will make your calculation much more easier and much more, you will see, much more intuitive. Okay, so that's it. I already did this, so we can go to our data table, and we can check which parts of the system are gravity and which parts of the system are pressure. Also, what I did in this drawing, I used something that is called saved selection sets. We didn't talk about this, but I will show you how they can be created. So you can, for example, assign this data, gravity or pressure or anything else. And you can, for example, I will select all the data that are pressure, and the right mouse button, you can put it in the selection. And when I put it in the selection, the next time I go here to selection options, I can use this last selection. So last selection is something that you put in your selection. And you can see now I have only the pressure here. And if you want to create and save selection sets, you go here to this function, selection sets. You can select anything. You can select your last selections. You can select something with the CAD, something with Urbano selections. You can give that selection a name and you can save it. And here you can see that I prepared some selection sets. Just the pressure elements, just the gravity elements, just the pressure pipeline nodes, just the revision manholes from the gravity network, and this is the pumping stations. We have 15 pumping stations. So in Urbano, to have pressure pipelines, you don't have to assign any equipment. You don't have to make some nodes to be pumps, nothing like that. You just define what parts of the system are pressure, and also you can put for your pressure stations, you can put just some different blocks using styles or using labels. So that's how we do it here. Okay, so let's now open our data tables now that we know about selection sets, and I can show you. So the entire system, if we go to recapitulation summary, is approximately 12.5 kilometers. And if we go to saved selection sets and select just the pressure pipelines, just the pressure branches, we can see that in total, we have almost 2 kilometers of the pressure pipelines. In total, there are 15 pressure pipelines. That's how I named those pipelines as well. Okay, let's draw one profile for the sewage system, and nothing is stopping you to draw your profiles from any node to any node, and you can go in any direction, and you can also go through different types of the system, through the gravity networks and through the pressure pipelines. Let's draw this profile here, and you can also see that you can put this system type data in the profiles as well. So we see gravity, pressure, and so on. We do not have any pipe invert defined yet, so let's do it. Again, I will do it by using automatic invert calculation. We define minimum and maximum depth below terrain, minimum and maximum slope. I will select the whole system, run calculation, and apply it. And you will notice that this function, even though I selected the whole system, will not calculate invert elevations for the pressure parts. It will skip it, and it will start again as it's the beginning of the system, as you can see. And that's it, because for the pressure pipelines, we can just go to input, we can go to input invert elevation, and again, I will use saved selection set to select just the pressure pipelines. Okay, and I will say that the invert position is in a constant depth below terrain, let's say 1.1 meter. And let's click save. Okay, the profile will update, and now we see that for the pressure pipelines, for the pressure branches, we have constant depth below terrain of 1.5 meters. Okay, also, let's now go to flows. Let's go to flow calculation. So Canalis, flow calculation. Not to be too repetitive, I already did this, so I will just show you. I calculated percent calculation. I defined this number because this is really small village. But the thing is, when you are calculating or assigning flows, be sure to define those flows just for gravity part, because of course you will not have the section flows for the, let's select everything just to show you. For the, if we go to this pressure pipelines, we see that we have nothing defined. Through the pressure pipelines, only the transit flow will go. But this flow that is generated, it is generated only on the gravity parts. And also, I defined some point flows, and I defined those point flows. If we check it, I defined those point flows to the first sections of the pressure pipelines. And why I did it? Because when I calculated the flows, I got really small flows in some of the pumping stations, in some of the pressure pipelines. So of course that I will not size these pressure pipelines to flow of 0.01 liter per second. So that's why I assigned some point flows so that the total flows, if we go to total flow scenario and also go to this, let's check this point flows. I wanted that each pressure pipeline has the total flow of at least 5 liters per second. So that's it. And now you see these are the total flows and the maximum flow is 42 liter per second. Okay, so now we have everything to size this network. Okay, let's go to first function for hydraulic calculation in gravity network. We will use option for pipe sizing. Let's use for the pipe group, let's use this my PEHD pipes, for example. I will leave this fixed percentage to 80 and I will leave minimum pipe diameter to 200. I will select the whole system, calculate and save, because I'm in the function for hydraulic calculation in gravity network. So only gravity network can be selected and computed. We see filling percentage is smaller than 80, so that is great. Let's click close. Let's go to our profiles and we can see how the gravity parts are now sized. We have the pipes, we have the filling of the pipes as well. Let's now do this for the pressure pipelines. And for the pressure pipelines, we have to go to different function, which is called hydraulic calculation in pressure pipelines. And now you see why it is good to have each pipeline as one branch, because then you can do it like this. Because inside of a one branch, if a flow is constant, we have only transit flows, we will have the same velocity inside of that pipeline, we will have the same diameter in that pipeline. So you can check it like this. We have in total 15 branches, we have 15 pipelines. And how this calculation is going, it's a little bit different. So you have to define what is, so for the flow scenario, it can be sum of all defined flows or total flow scenario, it's all the same. We will do pipe sizing. Also, you can assign previously the pipes and just do it according to existing diameters, but we will do pipe sizing. Formula will be Colebrook-White. You have to select a pipe group, of course. So I will use some water pipes, some, again, PEHD pipes, but with the nominal pressure 10. This is just the data. You can select any pipe group. Okay. Some parameters, you will use local losses as 10% of linear losses, and target velocity, I will say 1.5. That's it. Calculate, save. So what the software did here? So we have the invert starting and ending invert elevation of the pressure branch, pressure pipeline. We have static difference between the elevations. We have total flows. We have target velocity. Based on this target velocity, the software calculated minimum requested nominal diameter, inner diameter of the pipe. It went to the pipe catalog, searched for the first bigger pipe, and for that pipe, it calculated real velocity inside of the pipeline. And we see that the velocity is real close to our targeting 1.5, which is great. And all other parameters for this calculation is here. We see roughness, we see Reynolds number, this is the Darcy friction factor, linear losses, local losses, total losses. This is the velocity, energy line, and also we see the manometric heights, which is the input parameters for picking of the pumping stations. In Urbano, we don't have anything for any except for this. We are software for calculating the pipes, so we cannot size the actual pumping stations, but this is great input for your peaking of the pumping stations. But if we save this, we already did, we can go to our profiles and we can see that now our pipelines are completely sized. Of course, the filling level inside of the pipelines are 100%, but all the pipelines are calculated. Okay, let's also put some of the labels here. I will turn off just the layer with this stations, so not to have too many labels. And let's apply this label, diameter, flow, and velocity, but I will apply it only to saved selection sets gravity, like this. You can see diameter, flow, and velocity. And for the pressure branches, I will use the branch label. It's array label, but set to branch. Double click. You can select all the pressure branches, but I like to do it interactively. So I will pick one label here, one label here. And you have the name of the branch, length, nominal diameter, flow, and velocity. And now you can pick on each branch interactively. There is 15 of them. I will not mark all of them, but it's really nice label to do it manually like this. Also, we can create all kinds of reports. So we can go to previews for section hydraulics. You can also select just saved selection set for the gravity network. And this is it. This is all the data that you need for your gravity sections. And also we can select only pressure pipelines like this, and we can switch to data group, data configuration for pressure pipelines. So pressure branches. That's why I say always do one pressure pipeline as one branch, because the data for flow, for diameter, flow, velocity will be the same in this whole branch. So you can do it like this, and all the data is here, just like we had it in the function. You can copy it, you can go to any of your Microsoft applications, and you can paste it there. Okay, let's save this. We will save it as final. And I just realized that I wanted to show you one more thing. It will be really quick. I will open again this IDF method. I will open this final tool, and I will show you one very quick function, and that is export to SVMM, EPA SVMM. We can only export, we cannot import. So, but you know that it's really hard to draw in hydraulic modeling softwares and define some elevations precisely, set flows and stuff like that. So of course, if you are planning to do hydraulic modeling after this detailed design process, you can define everything in Urbano. You can set the pipes, you can set the flows, you can size the network, you can define catchment areas with these intelligent functions, and then you can go just click on Canalis panel, write EPA SVMM file. Okay, we will do it here. Select, okay, the file is written, it is here, and now I will just open SVMM. Okay, let's drag and drop this file, and this is it. So just imagine how much time would you need to create this in SVMM. And it's not just the visual. We can also zoom, for example, here. I can select a catchment. Of course, in SVMM, you have many different data we don't have in Urbano. So the default will be set. But for example, for the sections or conduits, everything is here, like invert elevations, like I don't know, types of the pipes, sizes of the pipes. You can also pick on a junction, and also invert elevations, depths of the manholes. Everything is here. Okay, so I extended 5 more minutes because I wanted to complete everything that I plan to show you during this 3 days of the training. I hope you liked it. I hope you would like to test it and try it yourself. And of course, we are here for additional help for you, for any questions that you might have.